everybody. Today we're going to talk about the fundamental theorem of arithmetic with, shockingly, still me. Now the fundamental theorem of arithmetic is what gives us that every number has a unique prime factorization. For instance, we know that like 12, we can do this little factoring thing. We can get down to here. 12 can be written as 2 squared times 3. There is no other way to write this using prime numbers, and it is so intuitive that some of you may have tried to use this earlier in the semester. They're going, well, it's logical, right? And be like, yes, it is, but we do have to prove it if we want to be able to use it. And so that's what we're going to do today. So fundamental theorem of arithmetic says that every positive integer n that is greater than 1 is either going to be a prime number or can be expressed as the product of prime numbers. And then furthermore, this representation is going to be unique up to like order. It doesn't matter if we write 2 times 3 times 2 or 2 times 2 times 3. Like, we don't care about the order. Okay, so the very first thing that we have to do is we have to prove that it's either going to be prime or the product of primes. In order to do this, let's put down a goal. So I want to show what are we assuming. We're assuming that we're working with an integer. And we're assuming that integer is greater than 1. And what we want to be able to conclude is that this integer is either prime or the product of primes. All right, so then now that we know like where we're going, let's start up with our proof. So proof. Suppose we have an integer and suppose that it is greater than 1. Now, what kind of proof goes with integers, specifically positive integers? Induction. So we are back all the way to the beginning of this class when we did induction, and we loved it then, right? So how do we proceed with this? We have base case, we have inductive step. So let's do our base case first. The base case, the smallest one that we can come up with. So what is the smallest integer bigger than 1? 2. Is 2 either prime or a product of primes? Yes, yes it is. 2 is prime. So we are done. So next, we have to do our inductive step. Remember, for our inductive step, we assume it's true for n, and then we prove it has to also be true for n plus 1. So inductive step. So assume our assumption is true for n. Now we need to show that it is true for n plus 1. Our assumption being, let's write it down real fast. N is either prime or n is the product of primes. Okay, so now we're going to do this for n plus 1, and it's like, well, it depends. What's going on with n plus 1? There are two very different things that could be going. Maybe it's prime, maybe it's not. Let's do cases inside of our induction, because why not? Case 1, n plus 1 is prime. Well, if it's prime, we're done. So then the other case is it is not prime, and I need to show that it can be expressed as the product of primes. So what does it mean to be not prime? It means n plus 1 is composite. So we could say that there are two numbers that are going to multiply together to be n plus 1. So there exists an a and a b in the integers. A and b will be between 1 and n plus 1. Such that n plus 1 is equal to a times b. No, we could choose to write this as 2 less than or equal to a comma b. Okay. Because a and b are not going to be 1 or n plus 1. Otherwise, we would be back at prime. Okay. So since we can say that n plus 1 is being written as these two numbers a and b, we know from our assumption that we can write these guys as being products of primes, right? Let's track back to our assumption. Like, sort of. We know that n can be written that way. So really what I do is maybe I don't want to make this assumption for n. Maybe I want to assume it for more than just n. That way I can use it for a and b. So for 2, 3, all the way up to whatever n is. And now a, b, which are sitting here, they're less than or equal to n. They're somewhere in here. I can express them as being either a prime or a product of primes. So I'm going to write then a equals, and we'll say it's we'll say p1 to the k1 power all the way up to, we'll say we've got m many, and then b can be done with q's because why not? So we'll say p, k, no, not k, only. Okay, and this this writing out of a and b works because let's say you're like maybe they're not products of primes. What if they were just primes themselves and be like, okay, well then like km would be 0 and k1 would be 1. So the only thing is sitting here is whatever p1 is. Like it's still fine. Everything over here is definitely prime, is what this is guaranteeing us. So now let's write out what a times b is going to be equal to. That way we can get back to n plus 1. So then n plus 1, which is equal to a times b, is really just going to be p1 to the k1 all the way up to pm to the km times q1 to the l1 qp to the lp. Okay. So this is the product of primes. This is the product of primes, which means when we multiply them together, now we just have the product of more primes. So there you go. N plus 1 has been written as the product of primes in the case that it is not prime. And that covers all of our bases. And we can safely conclude that any integer can be written thus as either a prime. It is either a prime or it can be written as the product of primes. Now let's go back to our theorem. Let's go take a peek at them. Note that it says every positive integer that is greater than 1, it's either a prime, expresses the product of primes, but we have this extra thing that we haven't talked about yet. This representation is going to be unique. This is like the really juicy, powerful part of this theorem. And so until today, we haven't had the tools to prove this. This is what we were building our toolbox for last time. So let's go ahead and prove that this is unique the same way we always go about uniqueness, by assuming there's two of them. Suppose for a moment that n is equal to the prime factorization p1, p2, up to ps, but it also has the prime factorization involving these q's, where the q's go up to t. Now, either they have the same number of primes, or one of them has more. So we're going to say without loss of generality, s is less than or equal to t. For no particular reason, you can do t is bigger than s. It really doesn't matter. So then what we have is p1 times an integer is equal to this integer. That is the definition of divides. P1 is going to divide Q1 times Q2 all the way up to QT. This is the lemma that we just talked about. If you have a prime number dividing the product of primes, it's equal to one of them. So P1 is going to be equal to QK for one of these Q's. So 1 to T. It's equal to one of them. So what I'm going to do now is I'm going to be clever. I'm going to rearrange. I can spell rearrange. I can totally do that. It is in my skill set. Rearrange. So we have P1, P2 up to Pn is equal to Qk. I've moved, that's what I mean by rearrange. I want to move that Qk to the front. So then Qk minus 1, Qk plus 1, Qt. And then really, it does not matter what these indices are. I had them assigned at random. It doesn't matter how we label these. But some labels are more advantageous to think about. So let's go ahead and relabel so that we have P1, P2, Pn is equal to Q1, Q2, Qt, where to preserve the information, remember the important part was Qk was being divided by P1. So with this relabeling, P1 now divides Q1. Just now our indices match. That's why we did the whole let's relabel thing. Because now when we do this thing right here, now we can cancel off, and now we can say that we have these guys are equal starting at 2. And now it should become explicitly clear what we're going to do is we're going to take these steps and we're going to repeat them. So repeat steps star through double star. What that's going to let us do is then we're going to be able to cancel off the P2 and the Q2 because we will have proved that P2 is going to divide one of the Q's. We're going to relabel it so that it's Q2, and then we can cancel it off. And we can do that. Oops, I said N. That should be an S. Oh, I really just want to talk about N's, I guess. This is also an S. Yeah, I said the P's go up to PS. So since S is less than or equal to T, we're going to be able to repeat this until we get 1 is equal to Q, then S plus 1, because we'll have canceled out everything else. Qt, but that's only going to work, like this expression only works if S is strictly less than T. If S was equal to T, then we would have had the same number on each side, and we would have canceled out all the q's as well. However, we have that these are prime numbers. The p's, the p's and the q's were prime numbers. It was a prime factorization of n. So the only thing that q could potentially be like integer wise, so qj is going to be 1 from s plus 1 to t, but that's a contradiction. 1 is not a prime number. And so we don't want to include it in our prime factorization. So that means we can't have s is strictly less than t. So therefore, s has to be equal to t. And that's basically it. That's all of the pieces. We have the same number of q's as we do p's. And on top of that, what we have done is we have proven that, where did it go? P1 is going to be equal to QK, or once we relabel it, Q1. So then, what do we have? How did I say this? Then for all I equal to 1 up through S, we showed PI is equal to QI. So that means that we have one factorization, thus, because all the Q's and P's are the same, thus there is only one prime factorization of n, up to the ordering of the prime factors, which is important. It's background important because that's what lets us relabel everything there in that step. Okay, so that's the big thing about primes. Like we've been using it since grade school to do factorization trees, to be like, what are the prime factors of 24? That you go through and you build your factor tree and stuff. So we've been using it for a very, very long time, and now we've proven it. And that's all I have for primes, and I'll see you guys next time.